Hello, future engineers. Welcome to my YouTube channel. Here we are again of this video here, which presents the shear moment diagram construction, but this is the reverse because it is the moment diagram, the moment curve that is given, and we are required to construct the shear and the load diagram. So here is the problem. Given the moment diagram, and noting that the tangents at the left and right ends are horizontal, determine the maximum magnitude of the uniform load in the beam, the maximum value of the concentrated load, the maximum magnitude of the vertical reaction. So this is the given moment curve. And take note that we have horizontal tangents at the origin and at this highest point here and at this point here. So let's prepare the shear diagram and the moment diagram. First, this is second degree, and it begins with zero slope at moment. And remember, zero slope means in the moment curve means zero shear, zero value of shear at the start. And because this is second degree, it is first degree in the shear curve. Now, remember that the change in moment, negative 800 minus 0, is equal to the area of the triangle. So we expect that the shear diagram from the origin up to 2 meters to the right is a triangle. So we expect also that the shear at this point, call that shear 1, is negative. So that's 0, then call the shear ordinate here as V1. And by the definition, change in moment, negative 800 minus 0 equals area of the diagram above, so 1/2 of 2 times V1. So negative 800 minus 0 equals 1/2 of 2 times V1, so V sub 1 is equal to negative 800 newtons. Then between this point and that point, we have a first degree curve, so straight line. Then in the shear diagram, it is zero slope or 0 degree, or it is a rectangle. Now, negative 800, negative 80 minus negative 800 is positive, positive 720. So positive 720 is the area of a rectangle, which is also positive above the horizontal. So let's call the intensity of shear as V sub 2. And we equate the area V sub 2 times 1 to negative 80 minus negative 800, or 720. So V sub 2 is equal to 720. So we have constant 720 or 0 degree. The next, between this point and this point here, we have second degree curve. It is positive decreasing, and the shear at this point is 0. So we have 176 minus negative 80 is 256. Then that 256 is equal to the area of the triangle here, which is 1/2 of 1.6 times the height. And the height is, we will call that V sub 3. Then V sub 3 is positive because 176 minus negative of 8, negative of negative 80 is positive 256. So we will call that V sub 3. Then it is 0 here. So 176 minus negative 80 is 1/2 of 1.6, because this is triangular. 0 ordinate here because the tangent is horizontal, or 0 here, times V3. So V sub 3 is 320 newtons. So it is correct that the shear drops from V2 to V3. That's the figure. Then between this point and that highest point, we have negative increasing, or negative 400 minus 176 is negative 576. So this is second degree. So in the shear diagram, first degree, it is equal to, because it starts with 0 shear here, so it starts here, then it continues first degree. So it is equal to 1/2 of 2.4 times V sub 4. where V sub 4 is expected negative because negative 400 minus 176 is negative 576. So negative 400 minus 176 equals 1 half of 2.4 times V sub 4. So V sub 4 is equal to negative 480 newtons. Then between this point and the last point, the tangent is horizontal. Then we have another triangular loading here with the rightmost end at 0 because 0 shear, because 0 slope in the moment curve, and 0 minus negative 400 is positive 400. We expect a triangular loading here, and it ends here, and we expect that the shear is just to the left is equal to, so the shear here is positive because 0 minus negative 400 is 400, and it is equal to 1 half of V sub 5 times 2. So 0 minus negative 400 equals 1 half of 2 times V sub 5. V sub 5 therefore is positive 400. So this is the shear diagram. It is already complete with the ordinates. So let's now have the load diagram. So this is first degree, and V1 is negative 800 minus 0 is negative, and negative is equal to a loading which is downward. So we will call the loading rectangular loading because this is first degree, so we expect 0 degree there. So we will call the density as W1. We equate V1 negative 800 minus 0 to the area of that load diagram. So negative 800 minus 0 is W1 times 2. So W1 is negative 400 Newton per meter, or simply 400 Newtons per meter downward. Then there is an abrupt change in shear from V1 to V2. So there is an upward force here, which is the reaction, which is equal to V2 minus V1. So V sub 2 minus V1 is 720 minus negative 800. That would be 1,520. So the value of P1 is 1,520. So this is because we have an abrupt change. Then between 2 and 3, it's just straight. So meaning there's no load in between this point and the next point. But there is a concentrated load because we have a change in shear from V2 to V3. So V3 is 320, then minus the previous, which is V2, 720. So 320 minus 720 is negative 400. So that means there is a downward force of magnitude 400 newtons. So P2 is V3 minus V2 720, so negative 400 or 400 downward. So that's why we have P2 downward. Next, between this point and this point, we have 0 minus V3. We have another rectangular loading here, which is expected negative because 0 minus V3, 0 minus 320 is negative, and it is equal to W2 times 1.6. So again, 0 minus V3 is equal to area of the load diagram, W2 times 1.6. So W2 is negative 200 Newton per meter. So that means it is also downward. Then we have a first degree curve in the shear diagram. So it's 0 degree in the load diagram. So we have V4 minus 0. V sub 4 is negative 480 minus 0 is equal to W3 times 2.4, the area of the load diagram. So negative 480 minus 0 equals W3 times 2.4. Negative 480 minus 0 equals area of the load diagram. So W3 is equal to 200 newtons per meter. So they are just equal. Next, there is an abrupt change in shear. So V5 minus V4 because the shear is from V4 to V5. So there is an increase in shear, therefore there is an upward force there. which is equal to V5 400 minus V4 negative 480. So that's positive 880. So 400 minus negative 400 V5 minus V4, which is negative 480, equals P3. So P3 is 880 newtons upward. And finally, in this portion, we have first degree decreasing. So we have another uniform load there, which is 0 minus V5. 0 minus 400 is negative 400 is equal to W4 times 2. So 0 minus 400 equals W4 times 2. So W4 is also negative 200 newtons per meter, or 200 newtons per meter downward. So therefore, because this is already 0, there's no abrupt change in shear. So that's the load diagram, 400. Then the whole of this, W2, W3, W4 are equal to 200 newtons per meter each downward. So to answer the first question, the maximum magnitude of the uniform load in the beam, it is 400 Newton per meter downward. So Wmax is 400 Newton per meter downward. Then the next question, the maximum value of the concentrated load. So we only have one concentrated load, that is P2. So P2 is equal to 400 newtons downward. Then number 3, the maximum magnitude of the vertical reaction. So it's either P1 or P3, but P1 is greater than P3. So the answer is maximum upward reaction is P1, which is equal to 1,520 newtons upward. So that's it, the solution to this problem. So reminder, if you're still new to my YouTube channel, please don't forget to subscribe and press the notification bell so that you will be updated on my future videos. I hope that these videos are important in your studies. So I selected videos that are a bit challenging so that you will be prepared in your future life as future civil engineers. So thank you for watching.